Okay, this is the first hour of Physics 1B for October 6th. We're recording. And tonight we're going to be talking about heat transfer. Heat transfer is the process by which heat is transferred from one object to another. And these are the three methods of heat transfer we're going to talk about: conduction, convection, and radiation, with conduction being the first. So let's get right into it. So conduction is heat transfer due to contact between two objects. Like physical contact. The two objects have to actually touch each other. So for example, I have a cold beverage here. If I pick it up, it feels cold to me because there's ice in here, right? If you pick up a cup of coffee, it feels hot. And when you pick up a cup of coffee, you're feeling heat transfer from the coffee into your hand because your hand is obviously cooler than the coffee, right? That heat transfer always comes from a hot body to a cold body. And, there's a couple different ways that this can happen. It can happen between two different materials, or it can happen within one material, okay? So you could have a situation where, for example, you place two materials in contact with each other. Let's say one of them is at a very cold 10 degrees Celsius, and you take a hot object and you place it next to it so that it's in contact with it. And say maybe this object is, let's say at 100 degrees Celsius. Then there's going to be heat transfer that's going to go in this direction. And the colder object's going to heat up, okay? So direct contact, heat flows from the hot object to the cold object, and we call that conduction. Another type of heat transfer that can occur is, say, with a fire of any kind. So let's say you've got some logs here, and let's say that they're lit on fire. So we've got a nice flame here. So we've got this flame. It's above the fire. And let's say that you take a piece of metal and you stick one end of the metal into the fire like this here. And let's say that your piece of metal is, I don't know, maybe like a copper tube or something like that. Copper pipe, copper tube, whatever you want to call it. So when you place one end of the metal in the fire here, and here's you over here holding this object. Oops. So you're holding this, okay? And you're holding it in the fire, so your hands are touching right here. So what's going to happen to this copper tube? When you stick the copper tube in the fire, what's going to happen?
It'll heat up, and then the heat will transfer through the copper tube, and then it'll eventually reach you.
Exactly right. So it'll start off by heating up down here. So first thing that'll happen is that this side is going to get really hot. And then, because the pieces of the object are in contact with themselves, there's going to be heat transfer that comes up in this direction. And given enough time, the whole tube will be pretty hot because copper is a pretty good conductor of heat. And eventually you won't be able to hold it in your hands anymore, so you might need gloves or something like that to actually hold it after some time. Now this happens, this heat transfer, because it's a metal. And as you all know, metals are good at transferring heat. That's not very surprising, right? It's not surprising that if you take a piece of metal and you stick it in fire, that eventually the whole object will heat up, right? Well, what would be different would be, suppose that instead of that, I take a piece of wood and I stick it in the fire like this here. Well, wood's going to be very different, right? What's the wood going to do after some amount of time? You stick one into the fire, what's going to start happening down here?
It's just going to break apart.
Well, the end's going to start to light on fire, right? Or get really hot, right? In fact, it'll probably become red hot. The question is, will the heat actually transfer up to your hands, though?
No.
It won't, exactly. Now, of course, if the wood catches on fire and then the whole piece of wood catches on fire, that's a different story, right? Eventually, yeah, that would happen. But pretty much you can take a piece of wood and you can poke at the fire. This end right here close to the fire will get really hot. It may even become glowing red hot or something like that. But the heat doesn't really flow nearly as well through the wood, right? So your hand over here is not going to get hot. Now, there will be some heat transfer through this, and yeah, the piece of wood will get kind of hot just due to what we call radiation from the flames. But for the most part, you can hold this piece of wood in here forever until it burns up, basically, and your hands won't actually get hot. So what's actually different between the copper tube and the wood that makes this happen? Does anyone know? Why is it that this happens? Why does this heat transfer occur through the copper tube, but it doesn't happen through the wood?
It's a good insulator?
Wood is a good insulator. That's correct. Yep. And Jacob's saying it's something with the electrons in the material. That's actually exactly right. So it turns out to be the case that the thing that actually carries the heat up the tube are what are called conduction electrons. And the way it works is that copper is basically each atom of copper can give up one electron. So each atom, just think about it, that's a lot of electrons, right? There's within a copper tube, there's going to be trillions and trillions of atoms. And every one of those atoms has one free electron. So there's trillions of free electrons that are able to just move around in this wire. That's right, able to move around in the tube. And so those electrons will get really hot down here, right? And they'll start to move up to the cold side of the wire, or the cold side of the copper tube, and they carry off that energy. And if you take 1C, you'll learn a lot more about this. But what's interesting to say is that the reason why a copper tube conducts heat well is also the same reason why it conducts electricity well. It's these free electrons that can carry energy and move around however they like. In the wood doesn't give up free electrons to do this. And that's why wood doesn't conduct electricity very well, and it doesn't conduct heat very well, and so we call it an insulator. Okay, does that make sense to everyone?
That's interesting.
Yeah. Okay, so we know that heat flows differently through different objects, and because this is something in contact with itself, this is a process known as conduction, and we can actually quantify how quickly the heat flows through the copper tube by using something called thermal conductivity. And I have a list over here of different types of thermal conductivity for different objects. Now, what these tell us is the rate at which heat flows through the object. They have the units of watts, W is watts, which is power, joules per second, and then it's divided by meters and divided by temperature. Now, again, I hate the way they do this. These two are both in the denominator, but whoever wrote this book or whoever edited this apparently doesn't care about order of operations, even if we do. So both of these are in the denominator. Just looking at that just makes me so angry. Anyway, when we look at these numbers here, they tell us how well something is, or how well something conducts heat. And just in terms of the numbers themselves here, you can see that stuff like aluminum, brass, silver, all of these metals, except for mercury, and lead's pretty low. Which, if you ever touched a piece of lead, this shouldn't be too surprising, because yeah. But yeah, so stuff like aluminum, brass, and copper, they've got a really big number right here, right? And when we compare that to everything down here on the bottom, these are all insulators. So something like glass, it's 0.8. Styrofoam is one of the best insulators that we know of, and it has a thermal conductivity of 0.027. So that means it's really bad at conducting heat, which is a good thing when you want to keep something cold or when you want to keep something hot, right? If you've got a styrofoam cooler, you can throw a bunch of ice in it, throw a bunch of sodas in there, and they will stay cold for a long period of time. They'll get really cold. Vice versa, if you take a styrofoam container and let's say you've got a bunch of hot things something you want to keep hot, well, throw them in the styrofoam container and they will stay hot, because styrofoam is good at stopping heat flow, whether it be into your cooler or out of your cooler. If that makes sense. Other things that you can see here, there's like glass. Apparently, ice is a good insulator. And you all know what an igloo is, right? I say the word igloo. Do you guys know what an igloo is? Is that how you pronounce it? What is it? What is an igloo?
It's a cooler, right?
There are, I think, there's types of coolers that are named out of this, but Andrew's right. It's a house made of ice, or it's a home of ice. It's an ice fort. Yeah. So, it's literally a house that's made out of ice, okay? And I think they usually kind of look like this. There's like a dome, right? And then there's like a little entrance right here. It's kind of like a hovel in a way. And the entrance kind of comes out this way. I don't know how well I can draw it, but But yeah, it's literally made out of ice. This is like, is it, I don't know if it's, if I say that it's where Eskimos live, that might be kind of, I don't know. I shouldn't say that. So it's a home made of ice, basically, right? And you'd think, oh, well, if your home's made of ice, wouldn't that just be really cold inside? And the answer is no. Look, ice is actually really good at stopping the flow of heat, as it turns out. In fact, I think this is, maybe I'm probably wrong about this. I've never been to Alaska, but I think you can light a fire inside one of these things. I think. Maybe I'm wrong. I don't know. I know you can do it in a teepee, which is completely... All right, now I'm getting really... I need to be careful what I say. All right, so... anyway, ice is good at slowing down the flow of heat. Yeah, everything else is here too. Like bricks. You know, homes are made out of bricks, right? Sometimes they're made out of concrete. They do a good job of stopping heat flow. So if we want to quantify exactly how much heat flows through an object, we can use this equation right here. We're not going to derive this equation because my guess is that, yeah, you can make fire inside of an igloo. I thought you could, yeah. Oh, you're saying that fires inside igloos, they melt the snow inside slightly and insulate the igloo better. Yeah, that's interesting. That's really interesting. Huh. Okay, so this is our heat flow equation, and it's probably kind of daunting to look at right now, but when we do a couple problems, you'll see that this is really easy to use. So what does the heat flow depend on? Well, we know heat is defined by this symbol Q, right? So if I take the derivative with respect to time, now I'm talking about heat per second, okay? And the heat current, they call H. For those of you that have taken 1C, or those of you that have ever heard the term electric current, well, electric current looks just like heat current. Just like it. In fact, there's actually something called conductivity in electricity as well, and it's something that we can measure. And the values are slightly different, but the concept is the same. Actually, people that are in my 1C class right now just did a lab on Ohm's law, and this is basically Ohm's law. Right here, this is basically it, as it turns out. This is like current is equal to difference in voltage divided by resistance, and resistance would be given by these terms right here. So this is like, you know, when you actually get there, if I bet a lot of you who took physics in high school probably talks about Ohm's law. Voltage is equal to current times resistance. I bet a lot of you have talked about that before. This is the heat version of it, and they work exactly the same. It's literally the exact same variables that show up. The temperature difference gets replaced with the voltage difference, but every other term is 100% the same. It's even called current, heat current. The units are different. We even use the symbol Q for charge and heat both, which is interesting. So the equation looks almost identical, except instead of H, it's I. Regardless, sorry for that tangent, but it's always nice to know how everything connects together, because if you can learn how to understand this, it's going to help you understand electricity when you get there. If that makes sense. So what does it depend on? Well, it depends obviously on the conductivity of the material. The better the conductivity, the better the heat flow. So it's proportional to K. It's also proportional to area, and that's where we have this picture right here. So let's look at this picture. In this picture, what we have is a hot object, a cold object, and then the thing through which the heat is going to flow is this rod right here. Our rod has a cross-sectional area A, and that's the A that shows up here. The bigger the area gets, the more heat flow you're going to get. That should probably make sense. One way I can explain that is to say that if I touch my cup with a very small amount of area, like the end of my finger has a very small amount of area, there's going to be heat flow, but it's not going to warm my hand up very quick, right? Very quickly. However, if I increase the area of contact by putting my palm on here, now my hand starts to get cold really fast. And of course, the ice in here starts to melt more because there's heat flow from my hand now into the cup. The way I feel that is that my hand feels cold, so it feels like there's like cold flowing from the cup into my hand, but in physics we don't talk about the flow of cold, we talk about the flow of heat, right? So by increasing the contacts, I'm obviously going to feel the heat transfer more, and my hand will get colder faster. You can easily test that for yourself. Now, the other things that it's going to depend on are the size of the temperature difference. So the bigger the temperature difference between the two contacts points, like this and this, the larger the heat current's going to be. By having a really high temperature difference, that's like having a really steep hill, basically. If the hill's really steep, you're going to go down it fast, right? If a hill's really kind of like level, so the top elevation and the bottom elevation are kind of close to each other, you're going to very slowly roll down it. But if you have a really steep hill, you're going to roll down it really fast, right? So in that case, the temperature is kind of like elevation. So if this is 100 degrees and this is 0 degrees, you're going to get a certain heat flow. But if this is only 1 degree and this is 0 degrees, you can imagine that the heat flow is not going to be nearly as strong, right? Is that reasonable? The bigger this is compared to this, the faster it's going to flow. Does that seem like it makes sense to you all? Okay. The last portion is the length. So the longer that this rod is, the worse it's going to be at transferring heat, because you can imagine in the extreme case that if I make TH and TC really, really far apart from each other, it's hard to imagine that, it's easy to imagine that it would take a long time for the heat to pass through it. And so what's being shown here is that if you compare this picture to this picture where you've got double the length, the claim is that now doubling the length halves the heat current. And I think that should make some kind of sense too. And to compare this to electricity, the longer that a wire is, the more resistance it has to the flow of electricity. Okay, so that's our definitions. We're going to immediately just do a problem because it's the best way to understand how this works. Anyone have any comments or questions? Okay. Let's try to do this problem then. So we've got our equation up here, and here's the problem we want to do. It says a styrofoam cooler has a total wall area of 0.8 meters squared and a wall thickness of 2 centimeters. It is filled with ice, water, and cans of Omni-Cola, all at 0 degrees Celsius. What is the rate of heat flow into the cooler if the temperature of the outside wall is 30 degrees Celsius? How much ice melts in 3 hours? So we've got a cooler, and coolers have to be closed, right? So here's our cooler. So we'll draw it as like a box with a lid on the top. Right, so you've got your box, you've got your lid up here. Okay, do I really need to draw the lid? You guys can imagine that there's a lid here. I can just actually draw it like this. It's probably a lot easier. There we go. So you've got all your cola and your ice in here. So we've got the pieces of ice. We've got cans of cola. And what we want to figure out is if it's 30 degrees out here and it's 0 degrees in here, and I tell you the thickness of the walls, which we're going to call L, is equal to 2 centimeters, we want to figure out the heat transfer rate into the cooler. Because, say you're out at the beach, as it appears is what's going on in this picture right here, there's going to be heat flow directly into the cooler because it's colder, right? However, it's made of styrofoam, so that heat flow is not going to be super fast. So let's figure out exactly what that's going to be. Now they've drawn another sketch right here because we were told that the wall area is 0.8 meters squared. So what they've done is just turn that into just a flat kind of piece like this, and just say this is the hot temperature right here where the sun is. This is the cold temperature over here where the ice cubes are. And we're just going to use this data and figure out what the heat current is. So the heat current, which is also equal to dq over dt, is equal to Ka T hot, H is for hot, minus Tc. You're going to see these variables show up a lot in the next month or so. We're going to be talking a lot about heat transfer from hot objects into cold objects. We won't be using this equation a whole lot, although we will from time to time. But we're going to learn about how you can basically take this heat flow. Okay, this is why this is important. You might be asking, why do we care about heat flow? Well, it turns out that if you have a flow of heat in one direction, you can extract energy out of it, and you can make it do work for you. And every type of engine that exists, not every type, sorry, most engines that exist operate by using this heat current. So the internal combustion engine inside of a car, or the type of engine you have in a power plant that generates energy, which is called a generator, they operate off of this principle that heat always flows from hot to cold, and you can extract some energy from it. So that's kind of where this is all going. We're learning that heat flows in a certain way. We're learning how we can increase the rate of the heat flow. And then the next step after that is how do we harness the energy associated with it? Because then we can make things do work for us, which is one of the main things you do in physics and engineering, right? Is you construct objects like engines to help you do things like drive around town, right? So that's ultimately where we're going with all this, is to learn how we can do this and then also learn how we can extract energy from the flow of heat. Because the flow of heat's a flow of energy, and if we can just take a little bit of it, then we can get a lot of energy to power the world, and that's basically how most things work. Now, electric engines are a little bit different. Although, ultimately, a lot of electric engines are run off of burning fossil fuels, because that's how you charge electric cars, right? So, anyway.
Ironic.
Yeah. Of course, some people have, like, solar panels on their house, and they use the solar panels to charge their cars, and that's a pure electric car. That's, like, truly electric. Yeah. Okay, so let's go ahead and solve this. So we are going to need one piece of information from the table, which is we need to know what K for styrofoam is. I'll just call it K styro. For styrofoam, 0.027 is our thing. So this is 0.027 watts over meters times Kelvin. Okay. So plugging that in here for K, 0.027. We multiply by the cross-sectional area of the cooler, which is given in the problem to be 0.80 meters squared. We then multiply by the temperature difference here. So our temperature difference is 30 degrees for the hot minus 0 degrees for the cold. Easy to remember which is which, right? Because this is always going to be bigger than this one, which means this will always be positive. Finally, we divide by the length that it's trying to pass through. In this case, that length, which is the width of our walls, is 0.02 meters or 2 centimeters. And from this, we can calculate exactly what the heat current H is going to be. It's nice when they actually use the symbol. With forces, we always use the symbol F for force, right? It's nice that heat current is actually H instead of being some other weird thing, because sometimes, like, angular momentum is L, right? And there's all kinds of other examples of units that are really confusing, or symbols that are really confusing. So what do we get? Can you all calculate it for me? That's also what I got, 32.4. The units for this should be in watts. You can check the units here. This meter is going to cancel out with one of these. The other meter is going to cancel out with that one, so those go away. And then even though this says degrees Celsius here, you know that Kelvin and Celsius can cancel out as long as it's a temperature difference, and this is a temperature difference. So whether I put it in Kelvin or Celsius, it doesn't really matter. So that'll cancel out with kelvins, and then we just have watts. So that's the answer. It's going to be 32.4 watts.
Quick question.
Might sound like a... Go ahead.
So since the thermal conductivity of the rod material is always in meters times Kelvin, in all problems are we gonna have to convert the lengths into meters, or
Sure.
Can we?
Yeah, you will. That's right.
Gotcha.
Yep. Now this number, 32.4 watts, I don't know, is that a big number? Is it a small number? It's hard to know. I mean, we're not really good at watts, right? We probably don't really know what a watt is. It's 1 joule per second, but we don't really know what a joule is, so 32.4 watts. Is it a lot? Is it a little? Well, we guess it's probably little, because you can imagine if the container, instead of being made of styrofoam, was just a metal box that was made out of, like, silver, for example. Well, silver has this conductivity of 400, right? Which is roughly, let's see, call it 0.02. Jesus, how much bigger is that? 406 divided by this number. Let's do that. What's 406? Oops. Oh my god, why is it doing this? 406 divided by 0.027. That means 15,000. That's such a huge number. So if this was made of steel, we would get an answer that would be 15,000 times bigger. So to tell you what that would be, if I take 32.4 and I multiply by 15,000, oops, my answer would be 486 megawatts. That's a lot of energy. That's a lot of energy. You could expect that if this was a metal box, that the ice would melt extremely quickly, right? And that's what the next question's about, is how much ice melts in 3 hours. Because this can give us an understanding of just what this really means, you know? Because we can think about ice melting, you know? I'm sure that you have all, at one point in your life, reached your hand inside of a cooler. When you put your hand inside of a cooler that's been sitting outside for a long period of time, most of the ice is probably melted, right? Maybe not all of it, but some of the ice is melted. And so you have kind of an ice water bath and you've got some sodas in there or something like that, right? So let's see. How much ice melts in 3 hours? Can you all tell me, how might we do that? How could we figure out the mass of ice that melts?
We can use the MCAT equation.
Sounds good to me. That says that Q is equal to M times C times delta T. How are we going to get Q?
My bad, I thought.
Kate says H times T. Sure. If I take H and I multiply by time, that should give me the amount of heat, right? Now remember, this is ice melting, so are we sure this is the right equation? Or do we want to use the other one?
Hey, we would use the third one.
This one, right?
With the latent heat diffusion.
Because what's delta T right here?
It's 30 still.
No, that was for the first part of the problem. What's going on with the ice? Is the temperature of the ice going to change?
Yeah, it's changing, but it's also melting, so we do need to know.
It's not changing. Remember that when something melts, like ice into water, the temperature of the substance does not change. Because you still have ice and water together. The temperature will only go above 0 degrees Celsius if all of the ice melts. Only if all the ice melts. We don't need to use the MCAT equation. We can just use latent heat. So as Kate was saying, we can figure out the heat that's transferred in total by taking the rate at which the heat is transferred and multiplying by time. Heat times time should give you Q. So, putting these two together, we're going to have H times time is going to be equal to the mass of the ice that melts, multiplied by the latent heat of fusion for water. And solving this, we're going to get H times the time divided by the latent heat of fusion. Now, before we do, it looks like mice. Before we do this, does everybody understand the process here? And does anyone have any questions? If you don't understand where this comes from, it's a constant rate, so you can rearrange this equation as dq equals hdt, and then you could integrate both sides and you would get to this equation. Or you can just say, well, this is just the rate of heat flow. So if I take the rate and I multiply by time, as long as the rate is constant, that should give me the total amount of heat transfer. However you want to think about it. Okay, so H was 32.4. And that's in watts. So we have the time as 3 hours, but I don't know, what do you think? Should we convert the hours, or can we leave it like that?
We have to convert it to seconds.
We do need to convert it to seconds, that's right. I'm pretty sure this is the latent heat of fusion of water, but just to make sure, 334,000. Let's go back to last class. And we must have used it at some point. Here it is. Water, 334,000. That's correct. So that's the latent heat of fusion of water. So we'll put that down here in the denominator. And we'll multiply this by the conversion factor for hours to seconds. So the conversion factor there is going to be that 1 hour is 60 times 60, which would be 3,600 seconds, because there's 60 seconds in a minute and 60 minutes in an hour. And there we go. That should give us the mass of ice. Right there. Any questions? Okay, can you all solve it for me? What do you get? All right, so it's about 1.05 kilogram, which is about 2 pounds. Now, is that a lot? Is 2 pounds of ice a lot of pounds of ice?
No.
How do you know? I agree with you, by the way. I'm not disagreeing. I'm just saying, how do you know? You immediately said no. How do you know?
Well, I buy ice at the Dollar Tree. The pounds are 7-pound bags.
There you go.
Those go by pretty fast.
Exactly. So if you bought a 7-pound bag of ice and 2 pounds of it have melted, there's still 5 pounds of ice in there, right? So you got a good another 6 or 7 hours before it all melts, right? Which I can imagine it would be the case. Like, imagine you go to the beach in the morning, maybe like 10 a.m., right? Maybe you're having some kind of like beach party, and by the end of the day, when the sun starts setting, probably all of the ice is melted at that point, right? That's reasonable to think about. But it takes like all day long, like 12 hours to really melt up all the ice. Yeah. But you're right. That's what I would compare it to as well. If I go to the store and I buy some ice, you're going to buy it in 5, 10-pound bags. So that's not much, which tells you that, yeah, this heat flow is totally reasonable. It's not much at all. It will eventually melt your ice, but it's going to take a really long time. I like that problem. It's straightforward, it's simple, and it's relatable. So I think in that way it's a good problem. All right, does anyone have any questions?
Why was it mandatory for us to convert from hours to seconds?
Because watts is in joules per second.
Gotcha.
So that will then cancel out with seconds, and then if you check the rest of it, you have joules that cancels out with the joule from the watt, and you're left with kilograms that flip up to the numerator, so we get an answer that is in kilograms.
Thank you.
No problem. Good question. Any other questions before we keep going? Okay. The next thing we want to do is this problem right here. I'm reasonably certain you have some homework problems that look like this, so that'd be a good one to do. All right. This is the conduction through 2 bars. I'll tell you what. Because I really am supposed to do this, and I have not been doing it as often as I should due to the limited time we have, why don't you all read the problem and just try to kind of think about it, I'll give you a few minutes. Read it, think about it, maybe try to solve it. If you can't solve it, no big deal, you can just chill. But read it and think about it. That's all I ask that you do. Does that make sense? I'll give you 3 minutes. Oh, let me make it bigger so it's easier to read too. There you go. By the way, if any of you are watching the Dodgers game, I'm sure none of you watch baseball. Just whatever you do, please don't say anything about what's going on because I want to watch it after class. I'm sure if anybody here really cared about baseball, they probably would have skipped class tonight to watch the game, though. Your family's watching, Andrew? Okay. Just don't say anything. You got it recorded, Wallace? Good. Iowa football is ranked. Iowa football is really good. Yep. They're doing great. They got a big game coming up pretty soon, right? Against Penn State, I think. Yeah, that'll be a good one. Yeah, me too, Wallace. I actually vastly prefer to watch it later so you can skip through because you can watch the whole game so fast. I'm a Giants fan, but I really want the Dodgers to win, man. They had way too good of a season, and I think the Dodgers-Giants series is going to be freaking awesome. Really? It's hard to be an Angels fan. They're just so bad. We just have so many good players. It doesn't make any sense. They probably have the MVP this year. Oh, yeah. Yeah, clearly. Okay, I'll give you one more minute. Okay, that was like about 5 minutes, so hopefully that was enough time to get kind of think about the problem a little bit. What's wrong with being a Chargers fan? Chargers are really good right now. Oh my god, they're scary. Okay. Alrighty. So in this problem, we have this wall, and it's like a reservoir, and it has a temperature of 100 degrees Celsius. Over here, you have a temperature of 0 degrees Celsius. And in between, we have two bars. This one is steel, and this one's copper. The steel one is 10 centimeters long. The copper one is 20 centimeters long. And the diameter... Is it diameter? No. Okay, let's read it. Steel bar, 10 centimeters long, is welded end to end to a copper bar. Each bar has a square cross-section, so it's a square. 2 centimeters on a side. That means the area is going to be what? The area of a square, right? And the area of a square is just the square of the sides. So this would be what? 0.0004 meters squared. That might sound like a small area, but it's really just, 2 centimeters by 2 centimeters. I guess that's small. Area is kind of weird, though, because even though it's a tiny number. All right. The free end of the steel bar is kept at 100 degrees Celsius by placing it in contact with steam. The free end of the copper bar is kept at 0 degrees Celsius by placing it in contact with ice. Both bars are perfectly insulated on their sides. This is totally ridiculous. There's no such thing as perfect insulation. But, whatever. Find the steady... It's a physics problem. This is always what they do. Find the steady state temperature at the junction of the two bars and the total rate of heat flow through the bars. So those are the two things. We need to find temperature and heat flow rate through the bars. And the temperature we want to find is right here, right at this contact point. Okay, so you've all got had some time to think about this. How do you think that we should approach this? So far, the only equation we really have is this one right here. How can we make use of it in this case? Any ideas?
So I said H of the steel is equal to H of the copper.
All right, so... Sure, okay, so your theory is that... we're going to make it so that the heat flow through the steel should be equal to the heat flow through the copper. Why would that be? Why would that be the case? Can we say anything about why that should happen?
I mean, at a specific moment in time, they'll go through temperature equilibrium. They'll reach a certain temperature, right? Which will eventually equal each other.
Right. Whatever the temperature is here, I mean, they're going to be in equilibrium. That's right. Let me give you a scenario just to think about. Maybe this is what Kate was trying to type. I don't know. It looks like Kate's typing out something kind of long. Either that or you've changed your mind. The system is insulated, so they have to be equal. Okay. So let's suppose that I tell you, so this is steel. This is copper over here, okay? Let's suppose that I tell you that, let's assume that they're not equal and see what will happen. Let's see if that leads to an illogical conclusion. Does that make sense? So what if I told you that the heat flow here in the steel, let's say that this was equal to 10 watts, okay? And I tell you that the heat flow through the copper is equal to 8 watts, okay? What does that mean? That means that every second, 10 joules of heat is going into this point right here, where they meet, into that junction. 10 joules comes in. And how much comes out? If it's 8 watts, it would be how many joules every second?
8 joules.
8 joules. Anyone see a problem? Is that possible?
No, it's not possible.
Yeah, we can't just destroy the energy, right? This would be like saying, like, I have 10 pellets that come in this side, and only 8 pellets come out the other side. It's like, where'd the pellets go? Or like 10 little balls come in one side, and only 8 balls come out the other side. Where'd the balls go? Not only that, this is happening every second, right? Every single second, there's 10 something coming in and only 8 coming out. So every second, there's a loss of 2 joules every second, basically, right? And as Kate was saying, it's insulated. So we can imagine that this loss was due to energy being radiated out into the environment, right? But if they're insulated, that can't happen, right? It said somewhere here, both bars are perfectly insulated. So, due to the fact that energy has to be conserved, this isn't possible. Does that make sense to you all?
Yeah.
Okay.
I was also thinking that the temperature of the steel, if the temperature of the steel is going to be 100 degrees, we can, it's going to, since you're saying that, it does subtract a certain amount, which is going to be the temperature of the copper.
Right.
So we can say, like, the temperature of the steel would equal 100 minus the temperature of the copper, maybe?
You mean at this point?
Yeah, at that point. Well, actually,
you gotta be careful because what's going to happen at a certain point? It's probably gonna, maybe this point, yeah. What I would say is that the temperature of the steel is going to be falling until we get to this point here, and then the temperature of the copper is going to be falling until we get to this point here. It's my guess, but okay. So again, the way that we did this is I made the assumption that who was the person that said this? Was it Ryan? Who was it that said we should make that? It was Ryan, right? Yeah.
I have another, just...
Go ahead.
It goes against what I said, but why can you not assume that the energy is, like, going out of the system into the ice?
Oh, that it's going into the ice? Because I'm looking specifically at the contact point, because that's where the energy loss is occurring. You're absolutely right that energy could somehow go into the ice. If we made a connection, like let's say we made a connection with the ice, yeah, then I can understand that for sure.
Yeah, okay, that makes sense.
Or we could do what we're going to do later on, which is we could have a heat pump that pumps energy out of here, or a heat engine that takes the energy out. That's another possibility. But nothing like that's happening. So again, my strategy here was to say, let's assume that what Ryan said was wrong, and let's make it 10 watts and 8 watts, and that led us to a contradiction. So that's sometimes referred to as a proof by contradiction. Is that something you guys do in your math classes?
Yeah.
Yeah.
Proof by contradiction. Yeah. I love proof by contradiction. I think it's really neat. Okay, so we know now that our assumption is accurate. It must be the case that the heat flow through the steel is equal to the heat flow through the copper. And I also put this up here, just to remind you. It's also related to this. This is the Zeroth Law of Thermodynamics. Someone in my first class brought this up. That two systems are in thermal equilibrium if and only if they have the same temperature. So in this case, we know that this point right here has to be at the same temperature for both of them. And it also directly applies to this. Okay, so now we know what we need to do. We need to take our equation here at the top. So we're going to have... Oopsie daisy. Okay, we're going to have K steel multiplied by the cross-sectional area, which is the same for both. And then we're going to have T hot for the steel minus T cold for the steel. And what I'm going to do is I'm going to say, we already know that T hot for the steel is, what is it? This is going to be the hot side, right? So this is going to be 100. Whoops. This is going to be 100. And then we're calling the temperature at this point where they meet, T. So that's going to be the heat transfer through the steel. Hot side is going to be 100. Cold side for the steel is going to be this point right here, which is going to be this is what we're trying to solve for. And then in the denominator, we have the length of the steel. Okay, this should be equal to K for copper. Area, same for both of them. Turns out, I guess, no, we'll need this later, I guess. Multiplied by, and now for the copper, this is the hot side for the copper, right? And this is the cold side. So this is going to be our temperature T, the common temperature at the points they touch, minus 0. It is always really nice when you're doing problems and you get a 0 in there, because that means that anything that's multiplied by it is just going to be 0 as well. And then the denominator, we've got the length of the copper, which is slightly different. And now all we need to do is to solve for T. So let's do it. So we'll have, what I'm going to do first is just, we're going to multiply out. So K steel times, well, let's cancel out the areas. That will save us a lot of time. So K steel times 100 divided by L steel minus K steel times T divided by L steel equals K copper times T divided by L copper. And of course, if I multiply K times 0, I get 0. So that's the only term on the right-hand side. And now all that's left to do is just to group together the terms that have T in them, get them all on the same side of the equation. Pretty easy to do in this case, because all we need to do is basically just copy this, paste it down here, take out this equal sign, put the equal sign here, and put a plus sign there. Because all we've done is taken that same term and just added it over the right-hand side. Hopefully it's not too confusing if I do it that way. Hopefully you can follow the step from here to here. It looks really weird because the letters are exactly the same. But this is the equal sign of the second equation. And the next thing we do, of course, is to factor out the temperature on this side. I don't know if you all want me to do every one of these steps. I easily could have simplified this problem by just jumping to the final step, but I know that can be really confusing. Oh, you know what? This looks really confusing because this is supposed to be a subscript right here. I'll just make it a subscript. My bad. Okay, so K copper times, nothing, divided by L copper. There we go. That should be equal to K steel times 100 over L steel. Sorry, it gets a little bit illegible when I get to the bottom of the screen. And then we just need to go look up our numbers. So, tell you what, let's just copy paste this down here. So we got to that equation. Maybe I'll scroll up a little bit here because you can still see the work. Got that equation and we want to solve for T. So we'll do that by basically the same kind of way. We're just going to copy, paste, and we'll take that and put it in the denominator over here. Wait, we need to move this, I think, a little bit. Move it this way. And then we'll just increase this line And then we'll divide this whole thing here over to this side. It doesn't look the best, honestly. But, you know, I think you guys can follow along with what we've done. So that should be what the temperature is equal to. And then we just plug all of our numbers in. So K steel, 50.2. Times 100. Divided by L steel. Oh, what am I doing? I'm plugging numbers in now, I'm an idiot. Length of the steel was 10 centimeters, so this is 0.1. Times K steel, we said was 50.2. Divided by L steel, which is 0.1, sorry. And then plus K for copper is 385. So the rate of heat transfer through copper is much faster, and that is going to have an impact on what the answer is, as you will see. And we divide that by the length of the copper, which is 0.2. And that should all be equal to our temperature. Now, before we do the calculation, first of all, are there any questions? So my question now is, I've said before that it's okay to cancel Kelvin with Celsius as long as you have a temperature difference. It would appear as though we don't have a temperature difference here. So what do y'all think? Should we convert this to Kelvin? Should we maybe try it both ways?
Let's try it both ways.
All right, let's try it this way. Tell me what you get if you do this calculation, and then we'll do the same thing, but we'll put it in Kelvin. We'll say this is the answer in Celsius, and we'll say this is the answer in Kelvin. Okay, 20.7, that sounds correct to me from doing it on Monday. And now, what is 100 degrees Celsius in Kelvin? Well, you add 273, so it's 373. And so what do we get in Kelvin? Can y'all do it for me? $77?
Yeah, I got 77 too.
Whew, that's pretty cold. 77 Kelvin's pretty cold. Can we just do that? Is it just that simple? We know it's not right, because 77 is way below the freezing temperature of water, which would be 273. So what's wrong about what I just did? I know, but I want to hear you all kind of work it out. Because T cold was 273. That's right, Ryan. So actually, if you go back to our equation here, we would need to change this to 273, which means there would be another term right here that would be like minus K copper. This is what it would look like, right? If we did it in, you'd have to have another term here, which would be plus K copper over L copper multiplied by, instead of 0, you'd have 273 Kelvin, right? And then that would basically get added to the left-hand side right here. And then eventually you'd have to divide everything. So what would end up happening is you'd have another term up here. Okay, so I'm not gonna. We need to take a break right now, but it's just something to think about. I would encourage you to try it yourselves. However, I'm virtually certain that you get the same answer as we got here. Pretty sure that you would get the same answer. Okay, so we can't just do this. Can't just do that. That's not that simple. Okay, because we had already zeroed out one of the terms. Now I'm pretty sure that's a safe way to do it, but I would encourage you to prove me wrong if you can. All right, let's take a break until what, like 7:45?